3 o'clock here in the Netherlands, and when a meeting brings together Wilfred Null from SUS MicroOptic, Paolo Di Trapani from Coelux, or Wim Hertog from Osram, we know that magic can happen. So let's make MicroLED magic. Welcome back. Let's preview the online technology meeting for Monday, December 13th, kicking off at 3 p.m. Our focus will be on the success stories around micro-LEDs. It is fast becoming the leading flat panel display and lighting technology. But is it really a business for Europe? Based on the track record of the markets of current conventional displays and LEDs, some analysts have expressed doubts. But I am not an analyst. I am a realist optimist and a firm believer in the following concept. If you only make a prototype, it will always be difficult to scale it up to production in Europe. However, if you make a process or an automated machine to execute it, no matter where production is done, the final product will be powered by European genius. And this is the beauty of the current European micro-LED landscape. Micro-LEDs are already competing strongly against OLEDs and traditional LEDs, finding their niche where resolution is more important than size. Take the success story of Exceliprint, which eventually spun out their sister company, X-Display. As the pioneer in using microtransfer printing technology for the precise and fast pick and place of micro-sized components, they quickly raised money from industry leaders. They partnered with different equipment manufacturers like Epic member ASM Amicra. They built its largest and best microtransfer printing equipment and signed licensing agreements with global players. They will mass produce micro-LED displays using their foundational IP portfolio. With the entire world watching, they rose to the challenge. In my opinion, they set the path that European companies need to follow. Let's hear how they respond to the epic question. Micro-LED displays are based on crystalline gallium nitride and indium gallium aluminum phosphide semiconductors, and at Epic, we have mastered processing those. We can now achieve new levels of brightness and efficiency, which cannot be matched by OLED or LCD. I am sure in the long run, micro-LEDs will be less expensive than OLEDs. On Monday 13th, we will take a closer look across the micro-LED supply chain. So we have the companies making the substrates like IQE, the companies that are doing the bonding processes and the passivation like the newcomer from Finland, Comtech Solutions. Then we have the companies producing the active components like Osram, which makes us proud to be European. All of them are epic. Let's hear and facilitate fascinating success journeys, such as how MICLEDI, a spin-out of imec in Belgium, is about to revolutionize the augmented reality glasses market with the micro-LED display chips. And on the user side, what is the roadmap of Volvo towards accelerating the automotive take-up? Epic friend Paul-Henri Matha will tell us himself. So on lucky Monday the 13th, with less than 2 weeks before the holidays, let's turn on a festival of micro-LED Christmas lights. See you at exactly 3 p.m. And it is exactly 3 p.m. and you are all here to do business on micro-LEDs. Yes, indeed, I do have a lot of fun making these videos, but these videos have actually given us, Epic, the chance of speaking to the industry and sharing our passion for what amazing 3 last years we are living in the photonic industry. I'm so happy to see companies like IQE heavily invested on the VCSELs, on the materials 3.5 epi wafers for the VCSELs, looking at the micro-LED manufacturer. I'm so happy to have Phicon here, the company who doing the equipment manufacturing. Many of you already know the CEO award was given to the CEO of Phicon. All of us here looking to work together. So thank you, all of you. We keep racing. Every meeting is reaching 100 people online, plus thousands of you on YouTube. I cannot thank you enough for the great support that you have given to Epic over the last 16 years, but increasingly over the pandemic times. That has been fantastic. My name is Jose Pozo, and as usual, I speak on behalf of a fantastic group of 15 people who dedicate their life full time to the epic photonic industry, organize events, help you raise capital, provide access to the network. We had the biggest website to find a job in photonics, and we help you with market intelligence. Tracy Vanik is our head of photonic market research, and she's providing market reports. Have the report that we published last week on temperature screening. You will be truly amazed. What an amazing piece of work. But also today is the last but one meeting before the holidays. Season 5 is coming to an end. What an amazing feedback you have given us over the season 5. Everybody highlights the meeting on 3D printed optics. It was truly great. Today we have also a great meeting. We finish next week on the food and beverage. Just before Christmas, our last meeting is always on food and beverage for obvious reasons. But also remember that we already published last week the topics that we are addressing from January till the end of June. And today, many of you are addressing the topic of displays, the topic of lighting, so I made it easier for you. Highlight these 3 dates: lighting for automotive, 14th of February, 14th of March, Agri, Photonics, and 13th of June, Pixel Technology and Application. Highlight these 3 dates, but all of the others are also highly interesting. But most important, today, we are talking about micro-LEDs. So I would like, first of all, to acknowledge your cooperation. In life, nobody can do anything good alone anymore. It's true. Try. No, you cannot. Today, we are partnering with DVN, the leading magazine and publication for the automotive industry. Thank you very much for helping Epic reach the automotive market. I also would like to acknowledge our Maria partner, MicroOptics. Thank you for a great job you do promoting our activities worldwide. But most important, this meeting wouldn't be possible with the support of our sponsor today, coming all the way from Corning Laser Technologies based in Munich. They provide the systems for the glass cutting and also very active in lasers for the semiconductor industry, especially in the LED market. PI, coming all the way from Karlsruhe, they provide the automation and motion tools for the photonic industry. imec, the world leading R&D center on nanoelectronics and digital technologies. They provide state-of-the-art production for photonic industry. Excelitas, you're looking for a provider of detectors, light sources, optics. Excelitas is your partner of choice. If you look, a company that provides laser diodes and micro-optics comes to it, Focuslight. Thanks to the acquisition of Limo, they have now the real state-of-the-art for diode lasers, laser optics, and also any photonic application. Furthermore, one of the companies ahead of the European micro-optics revolution is SUS Micro-Optics, all the way from Neuchâtel. They provide wafer-level optics manufacturing, all the way from the Netherlands, from the beautiful city of Almelo, from the beautiful city. Avantes is here to tell us about the different spectroscopy solutions they provide in the visible for process monitoring. And last but definitely not least, Admesy is here with the colorimetry solutions to identify every color in any product-based production facility. All of these people are here with us, finding ways to do business. And with us as well is my co-chair today, Dr. Panagiotis Vergyris. Panos, what's going to happen over the next 2 hours? We may believe that Panagiotis is muted. So I can already tell you that over the next 2 hours, we are going to have the companies MICLEDI, Volvo, and CEA telling us about the challenges, but the purpose of this meeting is to make connections over the entire supply chain. So many of you are going to share one slide. Everyone in the room is welcome to share one slide at any point. All you have to do is tell us in the chat, and what we want to do is for all of you to answer the epic question, kind of thing we can do for each other. We have the automotive companies, so companies like Volvo in the room. We have medical companies like Merck. We have the possibility of working with equipment manufacturers like Ficontech, Micra, or Palomar. We have the possibility of helping the definition of materials, the definition of different laser technologies. All of us here looking for partners. As usual, this slide only corresponds to the companies who registered for this meeting. So you're an Epic member and you miss your logo there, that only means that you forgot to register. Don't let it happen again. Please register on time for any of the upcoming meetings. All the events are already announced all the way to June. And last but definitely not least, this meeting is live streaming YouTube. So hello, YouTubers on the wall. If you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-asset.com, and I will make sure to do the introductions. But just remember that if you have any questions, put it in the chat and I will read it in the room. Of course, also valid with the people with me here in the Zoom room. Use the chat. There is an internal chat. Use it to connect with each other. If you want to talk to Win Hertog from Osram, or you want to talk to Vicente Calvo from Comtech, write in the chat to each other. Use it because we need to connect. It's time to start. Time to start with this fantastic supply chain that we have today. We wanted to start with something quite fascinating. We wanted to start with the huge development that we have seen over the last years from a spin-off company of imec that has attracted the interest of the AR market by providing micro-LED solutions for the next generation displays in augmented reality. We welcome to the room the CTO of MICLEDI, Soeren Steudel. Soeren, thank you very much for being with us. Thank you well for your time. Thank you for your time, the floor, and the attention of everyone goes to Belgium, goes to MICLEDI.
Thank you very much, Jose. I hope I can match your enthusiasm.
You're doing well. Just do it. Smile. Yes.
Okay. Please let me introduce our company and what we are doing and what we want to achieve, actually.
Perfect.
Yes. So my name is Soeren Steudel. I'm the CTO and co-founder of MICLEDI, and I just would like to give you a few impression what we are going to do and where we are right now and where we are looking for partners. So the market on which we are interested is basically augmented reality. So in augmented reality nowadays, as you can see here on the left picture, that's those quite big bulky headsets like the Microsoft HoloLens, which are at the moment used for industrial and military application. And the vision which everyone has is to go in the future to a rather sleek and lightweight consumer product. And I think a lot of companies have announced for 2022, 2023, 2024 lightweight consumer products that they want to go into this market, because the big vision behind everyone is, hey, what's the next behind the mobile phone? There's big volumes. What's the next, let's say, platform for interfacing with the internet? Now, in reality, what you want with augmented reality is here actually shown in the dream. You would like to overlay a virtual object and still see the regular environment, and the virtual object should be that it's real. It really looks like it's there. Of course, if you see this nice graph here from, in this case here, it's a graph from Magic Leap. One thing which is already completely neglecting there are some elephants in the room, and that is there are still solutions where nobody has a solution for. Is, for example, how to take account into accommodation and conversion, and how to take into account of occlusion. Occlusion means that you don't see through the virtual object, still light coming through the background. But okay, these are things on the optics system which needs to be solved. However, if you want to make the AR glasses small and lightweight and sexy, and of course, high performance, as you could experience like with a mobile phone, what you need to do in first is having a great display. And the display which you need for AR depends, of course, which optics solution you choose, but the majority of the companies now converge onto waveguide optics with pupil expansion. You need a great display. And the display is at the moment one of the really big, let's say, gaps. Because if you see here, this Microsoft HoloLens, for example, one thing which you see here is that it's actually quite darkened. The reason is because the displays nowadays are not bright enough to deliver enough light to compete against the daylight, because the whole optic system is rather inefficient. Maybe less than 1% of your light reaches the eye from the light which you send out by a display. So you need a very high performance display, and that's where we think we can make a difference. You need a display which is very compact with quite a lot of resolution, pitch below 3 micrometer, at least full HD if you want to have a 40-50 degrees field of view, otherwise maybe more. You need super bright 1 to 10 million nits. If you compare that with a mobile phone display of 500 nits, it's simply because the efficiency losses in the optics path. Certain things about the shape of the optics you need to consider. Very good efficiency, because otherwise you run out of power. Very good image quality. And image quality in this case translates as well into what CMOS do you need. You need an advanced CMOS node to compute all of that. And you need, of course, a price which can be matched for consumer product. So where we come in is we are MICLEDI Micro Display, and our goal is to create and sell business to business a micro LED module. And if you can see here, this is just a drawing of the module, which is our goal to manufacture. That's basically a component which we would like to supply to the companies who make AR headsets. Now, we are a spin-off from imec, made in 2029. We spun off. And the cool business model is based around that we want to make this light engine, but we want to make it in a fabless way. Now, the first thing is, if you do it in a fabless way, is there's no fab which can actually integrate micro LEDs in an advanced node CMOS process. So you need to have the process flow available, and then you need, of course, to design and develop the product. And that's where we come in, because we have a unique process flow which is based on how can you make a micro LED, which is a compound semiconductor, merge the process flow into a CMOS 300mm fab. And that's where we think we can make the difference, and where we can then get a better power efficiency, better image quality, and better brightness. And here on the side, you see as well actually some real samples from our lab. Basically, we process at the moment on 300mm using the pilot line of imec, and basically run 300mm wafers through this pilot line. And on the lower left, you see basically how it looks if you have a 3 micrometer pitch blue LED display. So it's one thing to, of course, develop the technology. The other thing is you need to make a product out of that. And the way we look at it, it's very simple. We think you need to have a 300mm process integration technology to be able to drive advanced node CMOS as the driver chip for the displays. Now that means you will not build our own CMOS fab for that, because a CMOS fab is very expensive. And for a dedicated technology development, you need at least 100 to 200,000 wafers a year. Otherwise, you cannot cost efficiently run a fab. So this is a giant investment. And if you would try to do that by yourself, this is rather hopeless. So the way it is, we approach everything. We use standard manufacturing equipment for the full process development. And our goal is to transfer everything into a CMOS foundry with, of course, some investments in tool upgrades. And that's where basically our business model is. We work together with API suppliers to create the best in class API. What we buy is actually 150, 200mm API wafers, which we can resize on a 300mm wafer. Because there is no 300mm API actually to run something in a 300mm CMOS line. And that's one of our core competences, how to resize and select the best quality API and to resize it to a 300mm wafer. Then transfer that into a CMOS foundry, and then run a foundry process flow, so that where we design the ASIC, subcontract the foundry processing, the testing, the packaging, and in the final end, we calibrate the display through, because you need a lot of, let's say, display level Demura calibration, and then ship those best-in-class products to our customers. And there we, in this whole supply chain, we are actually actively looking for partners to work with. Of course, the core is CMOS foundries, but as well in the domain of design, API quality, testing, packaging, as well as then the final characterization, calibration. We are open to collaborate with different partners and see how to bring our product to the market. And our market timeline, where we think the volume manufacturing should happen, is around 2025. And that's a short 3-slide, 6 minutes overview of where we are. And if you have any question, please let me know.
Thank you very much for a great presentation. You know, I do love when people just stop talking and they know the presentation is over. It was a really, really great presentation. The light engine for AR has been shown as a key market for micro LEDs, and thanks to you, things are moving into the right direction. I would like to have a nice discussion about this. You already answered the epic question very clearly in your slides, so let's try to find some partners. So at the end of the day, you make light engines and you use micro LEDs for the light engines display. This is a market that has demands today, and I'm happy that today in the room we have one company that in the last weeks have made an impact worldwide on light engines. Actually, we have in the room AMS Osram. Wim Hertog, good afternoon. Wim is unmuting himself. Wim, thank you very much for joining the meeting. I think you already know Soeren. We have been in previous meetings together. My main question here for both of you is this market, the market for AR glasses, is demanding light engines today or tomorrow. What is the state of the art and the time to market of the micro LED based light engines? Maybe I will go first to Soeren and then to Wim. Soeren.
Yeah, time to market is a good question. I think there is a chance that the first companies in this field will bring out the real volume product in smaller volumes, maybe end of 2022, 2023. Higher volumes that someone has really scaled it in a dedicated fab for real volume production, meaning millions of units a year, I think will not happen before 2024, 2025 timeline. And of course, until then, people need to live with existing display solutions.
Wim from Hertog, most important, I would like to know, because I know that your expertise is very much linked to another different business line, but what brought you, Wim, to this meeting? What do you want to learn from this community? What kind of cooperations would you like to start?
What I would like to learn from the others here is basically what they see as main applications for micro-LEDs besides display, whatever I was talking about. So I think it's important to see micro-LEDs as an emerging technology that not only has its benefits in direct pixel-based applications, but also can contribute beneficially to other applications and bleed over to other application fields. And that's what I would like to see. If we can somehow link the benefits of very small LED-based emitters to other product categories.
Thank you very much. And Wim, you are at the right place for that. We're going to have discussions on many different applications. Let me come back to you on this, Soeren. Soeren, on the market of light engines, there's other competing potential solutions, one based on LEDs. There are people who are proposing, even we had another meeting with a company in the Netherlands called Lionics that we're proposing silicon nitride waveguides to combine light from the standard light sources. If I know it's a difficult question, but how do you compare your solution to other potential solutions?
First thing you need to see is the alternative display technologies to MicroLED. There are many different approaches how you can make AR optics, but the main one is basically, which at the moment seems to win out, is AR waveguide optics with pupil expansion. And then you run simply in the problem of that only below 1% of your light reaches the eye. Now, if you want to go an outdoor display, that means outdoor you compete against 10,000 nits, you multiply by factor 100, you're in the range of 1 to 10 million nits, which the most display technologies like OLED or so cannot compete. So basically, if the winning technology is AR waveguide, that means a lot of the other display technologies like LCOS, like MicroOLED will not be able to go into this direction. Now, where we think the difference is to other micro-LED companies, it's we think about manufacturability. MicroLED is not only about the microLED for itself, how to get the best performance out, but MicroLED is as much about the driving capabilities and how to integrate it into volume production. And of course, one approach is to go for, let's say, a more LED fab compatible process, but LED fabs are normally 6-inch, 8-inch fab with rather, let's say, low resolution equipment. And then you still have the problem of how do you integrate an advanced node CMOS with it? Mm-hmm. And we think the only cost-effective way is you need to remodel the full process flow that you're compatible with an high-end CMOS process flow, because the CMOS backplane anyhow comes from a high-end CMOS process flow. Anything where you try to do something, let's say, die to wafer integration, this is not really for volume production.
I am quite curious to try to find your partners after this meeting, of course. You identify your products as fabless product, and I do like that very much. For many of the companies who are fabless companies, they do the design and they do the testing themselves. Is it also your case that you are doing the testing of the light engine module in-house?
That's our plan. At the moment, we have raised the financing to make the initial development of the 300mm process flow together with our partners at imec. But of course, in the moment where we come to the productization, that means the CMOS design as well as the final product test, we are looking, of course, for partners to do let's say, the development of the test and calibration equipment. The calibration for itself, I think we will plan to do by ourselves. That's at least at the moment in our business plan, because that's a very critical point to come to a good display quality.
There are two ways of doing the test. Either you do it yourself or you're relying on OSAT. And I do believe that at least from the beginning, you will do it yourself. And for that, we do have the entire supply chain to help you here. I have a few people who I would like you to meet. They're going to be very useful for you in these testing facilities. We have from Avantes in the Netherlands, Herr Lob. Goedemiddag, great to see you here. You heard what Soeren is about to do, which is to set up a facility to test the micro-LEDs for these displays on AR. How can you help?
Thank you for giving me the word. So yes, we are at Avantes and we make spectroscopy and light measuring is our business. And especially when I listen to Soeren, he is setting up his own testing facility because he wants to measure all different kind of parameters of the light coming from these beautiful devices. So they really need to integrate their testing solutions. That's where we partner often up together with our customers, with our original equipment manufacturer customers, because we can tailor and determine together what your needs are. Do you have your own software? Do you have your own parameters where you want to work with? So how can we interface with your testing equipment to make everything work? So that part, it's not an off-the-shelf measurement equipment, but determining together how we have to modify our equipment to best suit you.
We have reached a very important topic right now, which is how to test the micro LEDs. Here, your testing is based on spectroscopy, as you said very well, from your expertise, and I know you have done an amazing job on helping top manufacturers of pixels on their wafer level characterization. With your experience on the micro LEDs, is there a need to do accurate spectroscopy, or any kind of colorimetry base would do the job?
Expertise on that is a little bit on the thin side. That's also one of my intentions of tapping into this meeting to hear more about it, because it is really an upcoming market. So I do expect that you have to work with relatively low intensities so that it can be critical to make accurate measurements, that you have to have sensible instruments to pick up to determine the right parameters for you. But the expertise is not that big yet because it is an upcoming market, but that's something we want to explore together with our customers.
Anybody has experience on the testing of micro LEDs at wafer level? What kind of parameters need to measure? Let me go, because actually we have some of the key experts in EPIC on colorimetry in the room. This is Peter Karp from Admesy. Peter, goedemiddag. Thank you very much for joining the meeting today. Peter, you joined the meeting from the colorimetry corner. You are doing a great job on that. What experience do you have in micro LEDs from what you heard from the network, and what is needed to measure to accurately characterize or test these micro LEDs?
Depending on the brightness you have, you can use a colorimeter, or that has always the advantage when you have, when you need to measure very fast, then you can choose a colorimeter because you will get more light on just 3 or 4 sensors. And if you need to characterize a display more accurate, or not exactly more accurate, but if you need to characterize it spectrally, then of course you need a spectroradiometer. But with a high performance colorimeter with very good filters, the difference, especially after calibration to the device under test, will be very small between a colorimeter. The accuracy difference will be pretty small to a spectroradiometer, but there are applications where a spectroradiometer will be beneficial and others where a colorimeter will be better because of the higher speed.
Soeren, I have more. These are just 2 examples of instrumentation companies that can help you with the testing. We have a lot more. Is there any particular parameter that really you think we need to monitor when we're doing the testing of micro LEDs for your application?
You talk about two different things about. One is, of course, on the wafer level, and that's more about yield verification, so that you really can test on every chip, every single pixel, and a full HD display per chip has automatically embedded 2 to 4 million LEDs. So that's one thing, and that's about the uniformity and just good pixel quality. Separately is then, of course, after the packaging and after the display integration into the AR optics, where you really need to know the CIE coordinate at a different, let's say, target value for every single pixel, and then save that and use that for then later do the demurrer and the real-time chromaticity correction. And of course, you will not probably go for measuring wavelengths. You will look for something which is basically with a camera-based system where you look at the CIE coordinates of every pixel.
At the end of the day, the problem that you are trying to solve is more a semiconductor problem. So they are actually to have one of the key companies in semiconductor production in the network. Alexander Losin from Alos Semiconductor, thank you very much for joining the meeting. You have heard from different corners, from the manufacturer to the fabless company to the instrumentation companies. Could you comment on the testing of MicroLEDs from the semiconductor manufacturing side?
Yes, hello everybody. Thanks, Jose. Thanks to everybody for having this great meeting again. And I think a lot of aspects have already been mentioned. And from our perspective, it is really, in a way, if the starting material, the epi wafer, and this is where we come from, we grow GaN on silicon on 200 and 300 millimeter diameter. You need to basically match the analysis you can do on epi wafer to all the analysis further down the processing chain, and that is then on the chip level. And here we have seen very interesting approaches by some people measuring chips as small as just a few hundred nanometers across. That's the smallest chips which customers of ours are building, and then doing that with different techniques which are then more compatible to doing both the testing which Soeren referred to, sample testing. And then really also doing failure analysis, because the failure analysis for the micro-LED chips is not really completely understood, I would claim, not by everybody in the field, at least. And there's many different defects which you see today, which are not relevant in LED manufacturing, but are crucial in micro-LED manufacturing. And this kind of testing is not only testing of the electrical devices, but then also of crystal quality, and merging this data into a yield analysis. And we see that the epi wafer is the starting material, which can then enable that. And it starts, for example, with wavelengths, that you have uniform wavelengths across the wafer. We see this really as a holographic. You need to have it across the whole manufacturing line and merge the data with together.
Alexander, as a semiconductor manufacturer, it is great to have you in the room. There is a lot of people who want to intervene. I will give the floor to all of you, but Alexander just said defects in semiconductor production. And when somebody says defects in the semiconductor production, there is a company in EPIC that is making a big impact in the industry by reducing those defects in the passivation processes. And the CEO is here, Vicente, all the way from Finland, Comtech Solution. I think what Alexander just said resonated with you.
Yes. Actually, I was nodding with my head to what Alexander was saying. Yeah, exactly. There are a lot of many different aspects that currently in characterization are neglected. And one common way of doing this full wafer characterization of micro-LEDs is based on very simple photoluminescence, which we as a company we make a very deep an extensive characterization of single chips to characterize defects on sidewalls of these 1 micron LEDs. And we have something that we have learned is that by just basically basic photoluminescence, you miss a lot of information. So when you really want to see the variation among chips through the whole wafer with just these quick PL measurements on one spot in every single chip site, you are missing a lot of information. You cannot detect actually these differences, these dead pixels, etc. So there are a lot of things that need to be taken into account. And as you said, we are specialized in passivation for these devices, where the smaller you go, the most critical and most impact to this performance of the chips is coming from the quality of this passivation. And it's something that we are still developing our own processes to characterize these chips to the final, let's say, final quality, which is desired by the industry.
First of all, congratulations on the cooperation with River. Congratulations on how much interest you have got from the industry. Alexander, did you know about Comtech Solutions?
Yes, we do. Yes.
You need to start working with them.
We have met before, also in one of your meetings, but also offline. Yeah, I think their passivation, the whole processing is also when Soeren spoke about processing in CMOS lines earlier. I think they also have a lot of learning to do, and we see that the big equipment companies are also investing in the space, because all this processing of the nitride materials still has to be established in these facilities, at least to the extent which is necessary to really make this product.
Thank you so much for the two of you to be part of EPIC. Back to Soeren. Soeren, there is a question for you in the chat, a very interesting question, because they generated a bit of debate afterwards. Wilfred, from SUS MicroOptics, wafer level manufacturing of micro-optics, what's on your mind?
Yes, I was just wondering how efficient the optical collimation is. So you said you can channel the light a little bit, you can concentrate it or collimate it. So I'm just curious how you do this and how efficient it is. And
the efficiency, of course, has its limit. You are simply limited by the attendee of the light. And in the end, it will be about how big is the emitter size versus the lens size, which you can integrate. Now, in the end, depending on how you make the implementation at 3 micrometer pitch, you have an enhancement within the apex angle of maybe factor 2 to factor 4.
Okay.
So if you, the apex angle which you target is somewhere like 40 degrees, something like 15% of your light in a Lambertian emitter is within that apex angle. So if you then can basically enhance it by, let's say, factor between 2 and 4 in the most optimistic case, you basically, yeah, that's the gain what you can do within the apex, of course, only.
Okay, thank you.
In the chat, Wim Hertog from Osram had a really interesting answer to the question. I would like for him to voice it out. Wim, thank you very much for being with us again. What's on your mind? Wim Hertog? Yes.
Yes, so I answered the question. Should I ask my next question?
No, please go ahead and answer the previous question for the people who are not in the Zoom room and don't have access to the chat, and then you can ask your next question.
Okay, so there was a question regarding so whether if MicroLEDs or Lambertian emitters, and I just wrote in the chat that so that's not necessarily the case. So it depends a bit on the chip design and on the material system you choose. But typically the main issue would be, in my opinion, that you wouldn't have necessarily the same emission profile between your red, green, and blue LEDs. And so we're talking about a far field emission profile. And if you have different emission profiles between these different RGB emitters, then you would have viewing angle issues at the end on your screen. So you can imagine that if you display a certain color coordinate, let's say D65, it's measured 5 straight on, and when you view it from the side, because of these different far field emission profiles, this color coordinate will shift towards a different color coordinate, and this gives you viewing angle dependent color shifts, which is a pretty big deal, especially once you start working with optics in your displays.
That's do you think about a solution for that? Is there a way that we can circumvent this?
There are solutions also used in typical LED production. You basically have to somehow ensure that your emission profile becomes Lambertian, and this can be simply done by using scattering materials, or you can really work on chip level, on die level, to work towards similar outcoupling structures, for example. Mm-hmm.
We're going to have a different discussion about this, but I think Soeren wants to comment.
Yeah, of course. I would say dispersion materials to put the Lambertian emitter in would be, of course, against the purpose to be able to collimate as much light in a narrow apex angle. Otherwise, your efficiency drops. But you're of course right. You can you need to design the optics on the wafer level already into account, not only taking how much to get the maximum amount of light within your apex angle, but you need to basically make sure that for RGB, you match within the apex angle which you target, let's say, a uniform profile for all colors at the same time. And that's one of the, let's say, consideration which you need to put already in the design of the lenses for itself.
It's been a very exciting opening discussion. 40 minutes went really fast, but we identified already many room for cooperation. And Soeren, on this light engine, there is a lot to discuss. You are in the race as one of the front leaders already for who is going to develop the standard light engine from AR. And I hope that you reach the end of the line. You're doing an amazing job. I'm happy to have you in the network. I want to welcome, before we go to the next speaker, and everybody wants to hear the presentation from Volvo. I'm aware they are next, but to make the perfect introduction, I would like to welcome to the meeting Greg Troman, who is with the Fourth Dimension Displays, one of the key EPIC members that we have in the display manufacturing with ferroelectric liquid crystal silicon. Greg, thank you very much for being with us. Yeah, special light modulators are your thing. What brought you to this meeting, and what kind of cooperations can we start?
Well, as probably many of you, I know I've spoken to some of you directly, I think probably after the last meeting we had on this, but as some of you will have seen the press release, we're actually working on a 2K by 2K MicroLED micro display for a customer. And without giving, obviously I can't give away anything that's sort of proprietary on that. But what I would say is it's a lot more difficult than you think. And I would say the things that have really been difficult with it is getting the right pixel architecture to get a really good performance when allowing for variations in the material. That's certainly been a key thing. It's not trivial. We've done a lot of backplanes over the years, LCOS, OLED, transmissive LCD across the whole of COPE, myself and our colleagues in the US. And this is by far the most complicated backplane that we've ever done. And you know how we've had to do it. So it makes our Jose's put up our ferroelectric liquid crystal ones there. The backplane that we've done for MicroLED makes this one look simple, and that's not because we wanted to make it super complex. It's just what we had to do to get the performance out of it. So my only comment, I think, is really that we spend a lot of time on these calls talking about deposition of material and treating it as though it's a materials issue. There's an awful lot of micro display knowledge that has to go into it in terms of getting, you know, the right dimming range, the color uniformity, brightness uniformity, the right you know, spectrum from you know, gray level 1 to gray level 256, even just getting the data on when it's a high resolution one. So you know, I think we knew it was going to be complicated, but it's been even more complicated and challenging than we thought to do the design. I think that's probably as much as I can say without giving too much away.
No, but feel free to give as much away as you want, because this meeting is a family meeting. Thank you very much for this. After the next presentation, I'm going to come to you because I want to address with you and with the rest of the supply chain some of the challenges that we have, as it is the color stability, as it is the problem that we had with the right optics, and as it is the problem we have with the 3D packaging. Let's address all these challenges with you as the great system integrator. But before, and with no further ado, it is very important in the EPIC meeting to hear the end user side. So we go to the company that makes the most reliable and safe cars in the market. As a proud owner of a Volvo S60, it is my pride, my pleasure to announce EPIC friend Paul-Henri Matha from Volvo Cars. Thank you very much for being with us. The floor is yours.
Yes, thank you, Jose. So I've done some slides to try to show to everybody what are the usage we can have for LED, mini-LED and micro-LED for car makers. Yeah. And then just I put some sentences I found on your website about what we will talk today: automotive lighting, LED, micro-LED. So then I try to explain why it is quite important for us. So first, one slide I did, I think, last year in the same meeting. It was about the usage for micro-LED. So we have lighting on the left, we have signaling and communication, and we have also what we call road marking. And then I will try to explain a bit for each topic. So the first topic, it is lighting technology. So the target with micro-LED to have the best and the maximum light on the road, whatever the traffic, to improve safety. And then when we have a camera, for example, what we see, we detect with the camera one oncoming car, and then we will say to the car, okay, I want to put light everywhere excepted on this car area. And then you can see what is the feedback we will have and what will see the driver. So he will see the car, it will be in full high beam, but he will have what we call a black zone or keep out zone without light, and then you will not glare. So you can see, for example, on this picture on the right, which is a picture from Valeo, we have seen in DVN, I think, 1 year in Munich. And then you can see that you put light on the pedestrian, but you do not glare the cars. You do not put light on the oncoming driver. So you do not glare the car. So this is what we want to do with micro-LED. And then you can see what is a micro-LED solution. So I will not learn anything to you. And then you can see one LED split in different chip. And then what we see on the road, it is on the right. Indeed, we have this sort of scenario when you have each LED will put 1 pixel of light, and then you can switch on and switch off some pixel, and then you will put light where you want, and you will put no light where you want, and then you will not put light, for example, on the eyes on the oncoming car. So one LED in this case is 1 pixel on the road. So after that, we have a second usage, which is what we use for signaling function and communication. So especially we mentioned what we will use for displays. And you have seen in a lot of demo cars, a lot of possibilities with display for the rear, for the front of the car, and also to exchange some information with pedestrian, especially an autonomous driving car. And then when we talk about mini-LEDs, so we have seen also this year in DVN a presentation from Samsung, which was quite interesting. And then you can see the interest of mini-LED compared to OLED. And then you can also project some information in the rear lamp due to these displays. So the question is which technology we should select, and is it ready for exterior communication? And then we are not convinced that it is ready for external communication, especially due to the luminance we need for automotive industry and especially exterior light. So for example, the luminance for a display for a TV is around 100 candela per square meter. For a phone, what I have seen in iPhone, it is around 200 candela per square meter. But if we want to do a position light, a rear position light, so the red position light on the rear of the car, we need around 1,500 candela per square meter. If we want to do a stop function, it is around 10,000 candela per square meter. And if we want to do the daytime running light, so for the front with white light, it is around 15,000 candela per square meter. And then we know that we have some limitation with the current technology, and perhaps it will be difficult to reach this luminance criteria. And then also after we have some discussion of interest about efficiency, because what we know for efficiency today when we do an optical design on cars, it is what we have in the past about light source. So we have a bulb, especially halogen bulb with 20 lumen per watt, something like this. With xenon bulb, we were around 100 lumen per watt. And with LED, now we have 100 lumen per watt. We can have perhaps 120, 130 lumen per watt. But then we do not use only the light source because it is Lambertian output. So we have an optical system. And then we have some collimators, which is really efficient, but designers, it is not really trendy for them, these collimators. It is what we have in the past with the first Audi A4, for example, with the daytime running light. It is not exactly what we have today. Today, we have especially some light guide to do something very homogeneous, and then the optical efficiency is 10%. And reflector technology, it is in between. It is especially what we use for lighting system with reflector. And then the total efficiency, what we have today with LED is between 10 and 80 lumen per watt on the complete system. So if we develop a mini LED solution or micro LED solution, so the technology should be able to compete with the LED system total efficiency, so between 10 and 80 lumen per watt. If it is less than that, we will have some difficulties because today optical efficiency and power consumption is quite critical for car makers. Yeah. And then I have a last slide about LED, because we talk about mini LED, but also it was one of the topics was today about LED. And then what could be improved for LED? So the first topic is less thermal loss and more flux, because each time, so I present data sheet from Osram in this case, which is Osram Black Flat, but all the competitors have exactly the same problems. When we increase the temperature, especially the junction temperature, the flux is reduced. And then we would like to keep the same flux when we have high temperature. And also we would like to be able to have higher maximum junction temperature, because today we are limited to 130, 150 degree. If we could go to 200 degree, 250 degree, it was the case with the bulb, then we could reduce the size of the PCB, or we could avoid the high cost PCB material like AMS, or we could remove also the heatsink. And then it could be cost saving, it could be also weight saving. So this could be good. But I know due to a limitation with semiconductor industry, you have this limitation with 150 junction temperature. Also, what we would like to have is to have more lumen per watt. So to be able to have 200 lumen per watt would be good. But after, I know that we have a physical limitation also with the definition of the lumen. So this will not be possible. Also, what could be good for LED to have a standard packaging between all the car makers. It was the case for bulb industry in the past, but it is not for LED. So if I use, for example, Osram LED and I do a design of a headlamp with Osram, I cannot change to MiniLED or to Nicha. It is not the same packaging and not the same interface. So we have some limitation with standardization. And the last topic about LEDs is the lifetime, because in the past, the current lifetime was 10,000 hours usage, but now with full electrical car, we have seen that we have less limitation, and the car could be driven during 50,000 hours perhaps. So it could be good also to increase the lifetime of the LED and to go from 10,000 hours to 50,000 hours. So this was what I wanted to mention about LED and mini LED for end users like automotive industry. Thank you.
Well, Henry, you are an epic star, and thanks to you, thanks to your car, I am alive after a car accident a few years ago. So I have to say that every time Volvo wants to be in any stage, I will make sure they are there. We have a lot of people that want to contribute and talk to you about your presentation. Derema, Osram, PI, SUS MicroOptics. Let me start with imec. We have imec in the room, represented by Vlatko. Milosevsky. Vlatko, thank you very much for being with us.
Hello.
Tell us.
Hi. Well, I mean, it's impressive, both speakers. So the first speaker, Soeren, he basically said that if you want to be successful in micro-LED, you need to innovate on the process side. And the second speaker says, if you want to be successful using LED in application, you have to innovate on the optical design side. And this is exactly where imec tries to help. It's not easy to innovate on the process side because the commercial foundries are not so keen to play around, and the universities are too far away for, let's say, making a serious process that can one day go to the production. So that's why imec tries to build a bridge between the academy and the foundries by providing state-of-the-art 300 millimeter CMOS line, 200 millimeter CMOS line, and then for the optical design innovation, we have EVG, nano imprint lithography, working with 200 or 300 millimeter masters. So we are here to help you guys.
Vlatko, for 300 millimeter micro LED manufacturing that you already do, and Soeren is a success story of this. Vlatko, what kind of cooperations would you like to start after this meeting? What kind of companies would you like EPIC to introduce you to go to the next step?
If you need to make a prototype, but you don't know where, we can help you. If you need a help with your optical design, if you need a help with your CMOS driver design, we have a portfolio of patents for micro LEDs. If you need a design, not only the CMOS, but the TFT, we have a partnership with the TFT foundries, and we have also capability of producing TFT backplanes ourselves. Those are the projects that we can help.
Vlatko, what if I need for the European micro-optics revolution to have a semiconductor plant in which they could adapt the wafer level manufacturing of micro-optics for satisfying the need for the semiconductor industry?
So what we typically do is we typically can produce something like 1,000 wafers per month for a customer, and then we have a, let's say, partnership that we take you to TSMCs and others.
I think it wasn't clear. Like I have in EPIC some of the best in the world manufacturers of lithography solutions. Some of the best.
Yes.
And I want them to be in contact with the semiconductor industry. And imec for me is the stepping stone. I think I'm doing a bad job explaining this. I have Mark Verschuren from Skill, from Philips here in the room. Mark, could you tell us, I think you have one slide for us. Could you tell us what you do? And then I'll make sure that Vlatko understands how I want him to help us.
Hi, Jose. Thank you for inviting me. Let me see if I can share the screen.
Bottom of the Zoom window, arrow up, share screen. And then you have to select the window you want to share. Yes, you know the drill.
So you're seeing my one slider, I guess.
Perfect. If you go to slideshow mode, we can see it a bit bigger. If not, it's okay. It's
I'll just make it a bit larger. Yes. So yes, my name is Mark Verschuren. I'm the CTO of Skill Nano Imprint Solutions. What we do is we provide, say, a total solution approach for a customer-specific nano imprint process. Nano imprint is, unlike semicon, which is mainly focused on silicon, has a huge variety of applications. So you need to tune a lot more the tooling, especially the process and the materials. There's a lot more variety in the materials to get the best solution for each application. We provide tooling from 100 millimeter, 150, 200 millimeter wafers. And just recently, we recently installed and validated a 300 millimeter tool at a customer. So we can do up to 300 millimeter wafers. And our expertise is in tuning the process with the customer. Now I was asked to give what we could do for or potentially see the link with micro LEDs. On the top right, what you can do is you can directly grow deep red, for example, and directly grow green without having the stress introduction by the gallium incorporation. If you make your templating small enough, and I'm talking sub 100 nanometers, as you see here, you can directly grow at high temperatures, so you have good crystal quality. We grew deep red, like 800 nanometer emitting InGaN at 850 C. There's a huge amount of indium incorporated because the lattice is relaxed. So in the future, that would potentially allow you to directly grow an RGB wafer, which then saves you the issue of separating all LEDs and reconstructing them. There was a lot of discussion on the brightness and how to increase the efficiency of the LEDs. So normal LEDs, they roughen the surface, and actually you need a lot of optical travel to couple out all the light. And you don't have that luxury if you're talking about LEDs that are a few microns or even less. So you can think about doing, after you've actually made your LEDs, you can do wafer scale litho. You can work with polarizers and then use photon recycling. You can work with photonic crystals. So instead of having a Lambertian emitter, you already collimate the LED, the light, and thereby increase the efficiency a lot. What we can do is on the wafer, which isn't flat anymore, because we're not hindered by this flatness with our technology, you can define LED trenches that are sub 100 nanometers. On the secondary optics side, meta lenses are coming up, diffractive optical elements for beam shaping. We directly can pattern high refractive index, inorganic materials that are light and temperature stable. We do a post anneal of these materials for 300C. It's fully inorganic, so they will survive the harsh conditions on these very high flux LEDs. We've shown that we can do about 1 micron overlay in a single wafer print on 300 millimeter wafers. And very important for these meta applications, but also, for example, in the direct growth or the templating, is that the pattern variations that we have are less than about a nanometer or about 1 nanometer.
For me, this is clear. So 1 micrometer accuracy on 300 millimeter wafers. So I would like to hear from Vlatko. Vlatko, when I do have technology like this in EPIC, Skill is one of our top members when it comes to this. We really want to have an entry point into imec. What would be the possibility for us to work closer and to get this into a pilot case?
Yeah, sure. I mean, after this call, I mean, you can all contact me, and then we will look into your case, your problem, and then we will propose a solution for you. There's plenty of toolkits that we can offer.
Thank you very much, Vlatko, and thank you very much, Mark. I am truly amazed with what you are doing. I do have a lot of people who have questions for Paul-Henri Matha. The first one, we have Leonard Brunberg in the room from Derema. Leonard, please, thank you very much for joining the meeting today. What's on your mind? Leonard from Derema, I think we have you muted. Leonard from Derema. I think we have problems with hearing him, but I'm going to read his question for you, Paul-Henri. The question is, once you have all desired LEDs in place and you want the light emitted from this to perform at the very best, he will be happy to guide us for the lens molding conditions available. So what I would like to add here, Paul-Henri Matha, is that I have seen a major push for MicroOptics arriving into the automotive sector. Press releases have been from every corner. What is your current feeling when it comes to bringing this high-end glass-based microoptics for displays into the automotive market?
Yes, we think there is really a future, especially to provide the information, so to do communication, but we have still some problems with regulation. And then we have to be able to demonstrate that we will not distract too much. And this is quite a huge investigation we have to do with all the university and all the industry to convince Geneva regulation, especially, that it will not create too much distraction. But about the technology, I think the technology is here, so it is available. So perhaps efficiency is not so good today or performance, but the technology is here. So it is just a question of years now. And in 3 years, 4 years, we will see this sort of technology.
At EPIC, we are amazed on the development of microoptics in Europe, really amazed. It's like the biggest thing that for us has happened over the last 2 decades on photonics. I actually have Wilfred Null in the room from SUS Microoptics. And I would like for Wilfred, are you with us?
Yes, hi.
Yes, I would like for you to tell us a bit how you could help in this particular scenario.
Okay, thank you. Can I share a slide with this?
Oh, always. Every EPIC member at every EPIC meeting can always share one slide.
Okay, wait, let me get this. Okay. Can you see it already? Or
Crystal clear. Go presentation show mode, slideshow mode, so we can see it bigger.
Do you see the preview or the other one?
Perfect. We see it clear.
Okay, good, because here it doesn't work well. Okay, yes. So I know we do MicroOptics since some time, and especially for automotive industry for some years. And we do more what you see on the left here. So we have this chromium mask. We have these LEDs that are collimated, and then we create this pattern somewhere on the ground. So, but what I wanted to know is can we do this on a mini LED or micro LED level? So what you see on the right side. So this way you can drastically, I think, increase the efficiency. I think for micro LEDs, the lenses are very small. You can probably do that with nano imprint, like Skill just showed. So thank you very much for the introduction. This was great, and very good process. But if you go to micro level, the things become a little bit more complicated. And so we are very specialized in when it comes to micro imprint. So and using automotive qualified materials. But of course, the properties that were shown before, they're very tough to reach. So we work with material manufacturers to get the properties to this level. So the high temperature and high durability, high power of blue light. Actually, this gets always forgotten. So that means the materials, they should not only withstand the high temperatures, but also the UV or the blue light is also can impact the material quite much as well. So, but I think we can help here. We can do this, and we can also combine our technology to wafer level, of course. So we have all the wafer level equipment on 8-inch, and soon maybe even bigger, and that means that we can imprint directly on those wafers, and so that you have a single monolithic element that you can use. So my question,
yes, please go ahead.
So my question is, how do you see the role of these? I know there were recently, if you follow the news, the automotive news, there were two car manufacturers that come up with MicroOptics now in headlamps. So they were announced recently. So that means so there is apparently a market for MLA-based headlamps. And how do you see that, Paul-Henri? What is missing here, and how can this be combined with mini or micro LEDs?
So the MLA technology, we have two constraints. So the first is the cost. It is quite expensive. And the optical efficiency, it is quite low, I think 10%, something like this. So if we compare to do lighting with reflector technology, 50%, so MLA, to have a good beam pattern, for example, you need 50 watt, 100 watt. If you have a good optical system, you need 10 or 20 watt. So yeah, we have these two problems, cost and optical efficiency. But if you
how
can
do you know
improve
that the efficiency is so low? Have you done the simulations in-house?
No, but it is what I have seen with I know that for the moment MLA, we have it on BMW for the pedal light, and also Lucid is launching this technology on Lucid Air in US. And we have seen that with all our tier one supplier also that the optical efficiency is not very good. But I have not detailed knowledge to understand why. And perhaps you can improve this technology and to improve by 2 or by 3 the optical efficiency also. But for the moment, it is expensive and it is not really efficient.
Between these two success cases, Paul-Henri, I was also quite amazed that 2 weeks ago, right? Today, 2 weeks ago, we saw this press release from Genesis.
Yeah.
Also with the MLA for the 2-line front headlamps. I do want Volvo to implement this as well. Wilfred is the best person I know in the network for you to have some details about the efficiency, and I want this to happen. So I am gonna buy the two of you dinner, so the two of you sit down and make a nice discussion, which I think you should deserve. You should do. I have Paul, because you showed this fantastic slide during the presentation, and you said this is the state of the art that we achieve with LEDs. How we compare with micro LEDs, and when you put this, I look quickly to Wim Hertog from Osram, and he was happy. And he posted in the chat, I would like to comment on this. Wim Hertog from Osram, thank you very much for being with us. Tell us what's on your mind.
Yeah, so I want to quickly comment actually on the efficiency topic. So Paul-Henri, on your system analysis here, you show that you would need pretty efficient LEDs, right, to come to these numbers.
Yeah.
And the thing is that if I look at the current state of the art of micro and also mini LEDs, it depends a bit on the size. We are not there yet. So generally, micro and mini LEDs are significantly less efficient than standard full-size devices, and it's not an inherent issue, and I think it's something that can be solved in the future. So Mark already showed some possible solutions on the light extraction problem, and I'm sure that also epitaxy-wise there will be solutions to the issues that are there now, but this will take time. And I think at the moment and in the coming years, it will be very hard to reach the efficiency numbers that you are referring to with the small LEDs and the small devices that we are today talking about.
If that part of the problem is in the epitaxy, I of course have to, you know, when people read each other's minds, he was answering Alexander in the chat while I was actually writing to him. You have to comment now. Alexander, the epitaxy challenge together with the MicroOptics challenge can solve the problem for Osram and of course for Volvo. Alexander, what do you have in mind for this?
Yes, I can absolutely agree with the colleague from Osram. I think that is indeed a challenge for the small chips. We do see, though, that there's very interesting approaches, for example, from Comtech, which was also participating earlier in the call, on improving the performance of small chips with novel processors. We see that there's quite a bit of progress on the design of the chips. We see that also the precision coming from the CMOS processing can actually help improve the efficiency, even though you go to really small chips. But indeed, also with respect to the current densities, there's a challenge posed for these small chips. So you can ask really whether eventually it will be at the same level as conventional LEDs. But both are a moving target, right? Conventional LEDs continue to improve, and so do micro LEDs. So we are quite positive that we're heading in that direction.
Alexander, it's good that you answered saying that you want to improve efficiency. Vicente from Comtech can reduce the defects, and also Soeren from MICLEDI, because his technology is very close to CMOS solutions. So Wim, on there is a lot of partnerships that we need to explore. I'm really happy that after this meeting, Wim, you're going to be working with many of our members as it was your wish list in the beginning. But there is a person that has a question for you. Peter Karp from Admesy, what's on your mind?
I just had a short question to Wim. The theoretical maximum luminous flux you can achieve with a MicroLED is the same like for standard LEDs, or is it different from the physical point of view?
No, I mean, I'm not a 100% specialist in epitaxy design, but as far as I understand, it's basically the same as for larger LEDs. So there should be no major difference between micro mini LEDs and larger LEDs when you look purely at the let's say the internal quantum efficiency of your LED. So the light generated in the epi, the photons generated there. And also if we find a way to properly outcouple the light from the chip itself, then there should be no difference between small and large LEDs. No. So I don't see any major roadblocks that would hinder micro LEDs to eventually reach the same efficiency as our larger LEDs. Okay. But as I said, it will take time.
Yeah, very interesting. Thank you.
But Vicente, I have a comment because I think the main issue is the thermal specification, because we will go to derating because we cannot extract the temperature from micro-LED, because if we have too many LEDs, indeed. And this is a limitation.
Yes, so it's the thermal limitation comes from an efficiency difference, right? If your efficiency would be the same, then you would need less LEDs and less power to get the same, and you would not have this thermal issue.
Yeah.
It is so good to have Wing and Paul-Henri in the room. Yes, Vicente, go ahead. Your hand is up. The floor is yours.
Yeah, thank you. Yeah, I'm going to share actually a couple of slides showing
yes,
a bit exactly this problem we are talking about now. So the problem in micro-LED, one of the, can you see my screen? I need to change the display settings, right?
It is coming from Finland. It's not here yet.
All right.
It's, when you click on the button share screen, then later you have to select the window that you want to share.
I did that already.
Stop and do it again, because this thing is stuck somewhere in the middle. And after Vicente, we will go to Cliff from PI, who also has something to contribute.
Somehow I'm blocked.
Yes, stop and start again. You will see. In the meantime, and while I think we are almost on the way to solve it, I would like to highlight how interesting it is to have Paul-Henri and Wim at this meeting looking for partners from the end user and supply side respectively. And remember that the purpose of this meeting is to start cooperation. So if there is no follow-up after this nice discussion, I would consider that the meeting was not successful. Just for me, Mark Soeren from Skill, make sure that you get in touch with imec. Just for me, Alexander, make sure that you get in touch with Comtech. Soeren, just make sure that you get in touch with 4-dimension display. All of you have to work together. I think we may have Vicente still in the room, or did we lose him? Well, we come back with Vicente because what he was going to show us is very interesting for the efficiency point of view. I would like to welcome to the meeting Cliff Jolai from TI. Cliff, thank you very much for being with us. You told us in the chat you have something to share with the community towards potential cooperations.
Hi there. Yes, it's great to hear all the different technologies, and one thing that we just wanted to point out was that we've been involved in a lot of the sort of mass transfer, which seems to be a topic that hasn't been really mentioned, but it tends to be the topic that customers come to us to discuss. And I just wanted to show something that that we were doing in the automotive industry. For lighting, exactly what has been shown by Volvo. So we've had several companies come to us and ask us to look at the transfer of the LEDs, and they're asking really tough numbers. And so what we've done, we've produced an air bearing based system which gives us exceptional precision capabilities. But also an ability to take data from a camera system and a sensor system to adjust the tip tilt on the wafer chucks and allow the correct pressure to be applied when they're doing a stamping process. So I just wanted to make people aware that we're starting to be asked for these systems in automotive lighting applications. So yeah, it's interesting to see and hear that people are saying it's not quite there, but certainly it seems to be a big topic of interest. And just to say also, we've been looking at inspection systems for these devices once they've been made. So we're producing systems at tens of at the moment. So we're looking for that next step where they suddenly jump into the larger manufacturing. So just wanted to make people aware of that. And if you're interested to see what else we're doing in micro-LED, certainly in mass transfer, and we would welcome customers to come and talk to us about the issues they're having with mass transfer, because we're now in that second iteration of the problem with many of the customers. So that's really just wanted to introduce PI as a solutions provider for micro-LED.
You're doing a fantastic job there, Cliff. And I have to say that soon as we manage to arrange all our present meetings, the pandemic is not putting it easy for us. We have already our packaging and assembly meeting to be agreed to be hosted in Karlsruhe at the headquarters of PI. Thank you very much for that. And you should know that our epic present meeting on MicroLEDs will be hosted at CEA Leti in Grenoble as soon as we can finally get rid of this stupid virus that is making our life very difficult. Vicente is back all the way from Finland. I really want everyone to know about the defects and the increased efficiency. Vicente, let's try again to share the screen.
Yes, hi, sorry for that. I was.
Oh, no, don't apologize on behalf of the cyberspace.
All right, I'll share my screen there. Okay. I'll put in presentation mode.
After this, Volvo has a challenge for everyone, so stay tuned. There's something big coming from Paul-Henri Matha. Vicente, tell us.
So yeah, what I was going to say is that, well, in MicroLEDs, one of the main problems, and like I explained earlier, is really the quality of the sidewalls of the chip. When you make the sidewall of the chip much smaller, the influence of the defects in these sidewalls becomes more and more prominent. So here is high resolution TM images of actually 5 microns MicroLED. And usually you have a quite thick oxide layer around all the surfaces of the chip, right? And if you look even closer in 5 nanometers kind of a scale, you can see there is a layer of amorphous oxide, the native oxides on these 3 materials, which are basically a lot of atomic level defects. And that's creating a lot of efficiency problems like recombination effects, mechanisms, etc., which are having then indirect impact to the internal quantum efficiency of the chip. What we do in Comtech is trying to optimize this sidewall quality by making a novel passivation technique, which is actually an oxidation step, but we create very high quality oxide, very, very thin, with very low amount of defects. This automatically translates in here is an example of a red MicroLED, indium gallium aluminum phosphide, where we have achieved like 3 times higher efficiency, getting 3 times higher light output. Or if you want to drive to the original, let's say, light output, you can do it with 90 times less current density. About the size, here is also an example. In the gray colors, this is different gallium nitride LEDs with size. So here you can see kind of the peak efficiency for these different sizes. And then you can see how if you go smaller from 80 microns down to 5 microns, there is almost an 80% reduction in efficiency of the chip. And this is very related to these sidewall effects. With our technology, as you can see in the bigger size chips, we don't have so much improvement. Why is that? Because the effect of the sidewall is not affecting that much when you get bigger size. But in the smaller sizes, you can see that the improvement is really huge. So we can make a 5 microns chip to perform as good as a 40 microns chip if you have a very efficient passivation on the chip. This adds a lot of opportunities, like by making smaller chips. You can make first reducing a lot of costs because you can get much more chips per wafer. Then from display point of view, the display panel, like there was somebody from Copin discussing about the difficulties of making the panels and so on. Making much smaller chips gives you more freedom for the chip pixel architecture. You can have redundancy on the chips, so to prevent so much rework, etc., etc. So it gives a lot of benefits. And we see that currently we are with a display manufacturer. We have demonstrated how with only our technology, we have improved the efficiency of their chips by 100% compared to ALD passivation. Because ALD works a lot in light extraction efficiency by creating different kind of, well, a better extraction of the light, similar to optics kind of properties because of the reflective coatings, etc., etc. But with our technology, we have the impact to the internal quantum efficiency, which is basically what dictates most of the efficiency of the chips. And that's why we see that Of course, there are a lot of techniques how to improve the efficiency of the final display or lights, lamps using micro-LEDs, but we believe that the main topic should be still to work on the efficiency of the chip itself. And then on top of that, put all the optics and collimators and whatever necessary. And
like every time you speak, I get a lot of compliments in the chat. Like Wim Hertog from Osram, he told me that this is really, really interesting. Alexander Lossing, he's saying, I love this. This is the perfect answer for the efficiency problem. Thank you very much, Vicente, and congratulations on what you are achieving. I promised I had to deliver. Paul-Henri Matha from Volvo has a challenge for the EPIC community. Paul-Henri, what's on your mind?
Yes, my question was, can we do a mini LED which is transparent, and then you can do different functions? So you can have one layer of function with this micro LED technology, and then behind this you can have another function like a stop lamp, for example. So if you are able to do this sort of solution, if you have some ideas, you can contact me. It is a good challenge, and it could be a lot of new design possibilities.
Transparent micro or minor LEDs to add another layer of functionality on top or underneath. I think that's the challenge on the table. Paul-Henri, I will promise I will collect information from EPIC and get back to you, because this is what we do, Paul-Henri, at EPIC. Panagiotis, Vergyris, my co-chair today. This is what we do, scouting the technologies and trying to find connections with the end users and with the supplying centers. Can you introduce our final speaker today, and let's find some more partnerships as the pilot production exceeds?
Yes, Jose, thank you, sir. The next speaker comes from the source of innovation in Grenoble, Kanaan Hani, and he's gonna speak. So now, Hani, are you here?
Yes.
Hani is muted.
Hi, everybody.
Hello.
Are you hearing me quite?
Crystal clear.
Yes, perfect. You can start sharing your screen.
No, yeah, I will share my screen. Do you see my screen?
Not yet.
What? Okay. We are good. Yes,
Yeah,
slideshow mode. Gorilla Glass clear. The floor is, no, you have to swap parameter d'affiliage. You have to swap.
Do you see my screen?
Yeah, we're seeing the wrong screen. We are seeing the screen that you don't want us to see. You want to see the other one. Just go to slideshow mode again. I will guide you. Go to slideshow mode and then go parameters d'affichage. There, the middle, that one, and then swap. Bascule. Mexi, the floor is yours.
Thank you. So thank you all for hosting us in this technical workshop. So today's my talk will be around could micro-LED technology bring the display industry back to Europe? It's a huge challenge, but it's very interesting. So first, I will introduce our institute in a few words. So LETI is based in Grenoble, France. We are around 2,000 people working within 10,000 square meters of clean room that include 200 millimeter and 300 millimeter microelectronics line with a annual budget around 300 million. What we do at LETI is related to almost every kind of technology existing that need microelectronics device integrated and miniaturized. So in terms of micro-LED, LETI is working on the micro-LED because micro-LED can serve two major kind of application. First, the micro display, what we call very small display below the field of the stepper. So for example, application like augmented reality, mixed reality, headlamp for automotive, or PUG for head-up display for automotive application, and all the other applications that have a bigger display size than 2 by 2 centimeter square, we call them for display application. Why micro-LED? Because micro-LED, as my previous speaker said, offer higher brightness, in theory, lower consumption, and could change the way of building display in our actual work. So in micro display, Leti choose to work on two approaches. One, the first, what we call hybridization or 3D integration technology, and the second approach is monolithic. Before I explain the difference between both of them, I would like to explain how we do a micro display. So as we are working on micro LEDs, so we will start from a gallium nitride epitaxy on a substrate. This substrate could be sapphire or could be silicon. From the other side, we need to build the drivers, which is the CMOS in our case. Usually it's built on 200 millimeter silicon or 300 millimeter silicon wafer. So we will take the epitaxy and apply microelectronics process on it in order to define the pixel shape and pitch. On the CMOS, we will have exactly the same form in terms of pixel shape and pitch. Then we will interconnect them by different technology. At this level, we will have a driver that can drive several micro LED. Based on the gallium nitride epitaxy, usually we will get the blue. Later, we need to convert in order to get the full color. So we can use different technology of color conversion like quantum dot or nanophosphor to get in addition to the blue, the green, and the red. And in some application, if we want to go further in the integration, we are able to curve our micro display in order to simplify the optical system. So the two main technologies that we are working on are first the hybridization technology. This technology, as I said, we have an gallium nitride epitaxy on a sapphire substrate or silicon. We will do the pixelization to define the size of the LEDs. And then we will interconnect this to the CMOS. This technology could be used for a chip-to-chip integration process, chip-to-wafer integration process. It's relatively flexible because it does not need wafer-to-wafer alignment, but it's limited on terms of resolution. With such technology, we are able to interconnect till around 10 micron pitch. If we want to go to higher resolution, in this case, we need to go for what we call the monolithic integration approach. And here, the difference is that we don't pixelize the epitaxy. We will transfer the whole epi to the CMOS that is already pixelated. And then we will do the pixelization process aligned with the CMOS last level. This monolithic approach allows us to work with 200 millimeter wafer. If it could be on silicon or sapphire, but the most of the time is on silicon, and also on 300 millimeter wafer. So we already had some result a few years ago with 2 micron pixel and size and 1 micron space between. So it's 3 micron pitch. You can see here some IV curve, IVL curve. And with the hybridization technology, we show some demo blue and green micro display. So those micro display can be used, as I said, for several applications like the AR, VR, like the headlamp for automotive, but in this case, we need white. We convert from blue to white. And also we can do full color projector for a head-up display inside the car. Now going to the big display size, and here this concept is the same. The idea is to use a CMOS to interconnect to the CMOS, the micro LED, convert the color, and then dice the CMOS to get what we call a smart pixel. And this smart pixel would be a block of interconnected CMOS to a micro LED. Then with a mass transfer process, we need to pick our LED, change the pitch, because on the wafer level, the density of the pixel would be very high. We need to pick them, spread again the pitch, and transfer to any backplane. And here, when I say any backplane, we need a large backplane. For example, it could be plastic, it could be metal, or it could be PCB. The idea is to have a backplane that is able to bring the power to the smart pixel. So, and with such process, we are able to really produce any size of display without using several billion of capex like the LCD and the OLED production line. Here with a standard microelectronics line, which costs several hundreds million of dollars, we are able to compete with several billions of dollar LCD and OLED display line. So what we already achieved in this field at LETI, so for the moment, we already have blue, green, and red smart pixel separately. And we already demonstrate a few proof of concept. What is under development now is to be able to do the smart pixels that contains the full 3 color, the RGB hybridized on the same CMOS, and then to transfer them, because this will allow us to reduce the step of transfer. And also what is remaining and challenging in this technology also is the color conversion. So also at LETI, we are working to find solution for native emission without using color conversion based on some same epitaxy. So this is a short state of the art of what we are doing at LETI now. Thank you very much.
Thank you very much, Hani. When I see this slide, I do love it. But my first question is: Are you already developing microtransfer printing process?
We are working on several aspects, on several approach. For the moment, there's several running on parallel, I can say.
Right. So the epic question comes your way. What can you do for the other 750 companies? And most important, what can they do for you?
What we can do for them, we are a technology supplier, so we are developing process and we can transfer those process in different field of application. What they can do for us, maybe we can find some collaboration on the transfer process, on the 300 millimeter gallium epitaxy on silicon to work on common process, because already we are working on 300 millimeter, because 300 millimeter in theory will allow us to reduce the cost of production by around 17–18%. So as you know, we are a RTO, we are open to any kind of collaboration.
In the beginning of the meeting, Hani, we saw the quick presentation from Mark Verschuren from Skill, from Philips in Eindhoven. The idea of bringing MicroOptics to the 300 millimeter plants is in the highest priority of the EPIC network. Would you be willing for a potential cooperation? Mark, are you still with us? Mark's still with us. He's smiling every time I mention his name.
Yeah, I'm here.
You notice that they are also transferring to a 300 millimeter. I really wanted you to interact today with imec and with LETI. Hani, would you be open for some kind of cooperation to bring MicroOptics manufacturing and metasurface manufacturing for a 300 millimeter plant?
Why not? Everything is discussable. As you know, we already have some activity in the fabulous European project on micro lenses on wafer level. So yes, it would be a very nice idea if there is possible collaboration on such subject.
I'll
contact you.
You need to get in touch with each other. One thing that I would like for everyone in a meeting like this one is to get to know each other. And there is a person that I don't think had the chance yet to introduce himself, which is a pity because I just lost him. All right, I just lost Paolo from Coelux, I believe. I know he's here. Paolo from Coelux is here in the room, and I would like everyone to meet them, because if everybody knows, the company Coelux is one of the most innovative companies that we have in the industry. I am quite impressed with the way that they simulate the sun into any room by making these amazing windows. And Paolo, what brought you to a meeting on MicroLEDs? And what kind of cooperations, challenges could you have with the rest of the companies in the supply chain?
We are very interested in cooperating. I actually have a question to the last speaker concerning the precision in positioning after the micro or mini LED are transferred in order to increase the pitch. So what's the final precision in terms of fractions of the micro mini LED size.
You are talking about the final pitch that we need on the backplane?
Yeah. Finally, you pick your mini or micro LED, displays them on a different pitch, but in a pick and place, let's say, approach, what would be the final precision in positioning, because they will be much more separated with respect to the other, and of course the collimation is highly sensitive to the positioning.
Yes, indeed. Actually, the final pitch is surely several times higher than the initial one. Now, what would be the interconnection precision? It should be around a few micron, let's say around 1 or 2 micron, not less.
Paolo, we really want to know more. Everybody is telling me that they want to know more about your challenges, especially with micro LEDs. So I'm sharing with you the homepage of Coelux, which shows this amazing windows that you have for indoor lighting. And could you tell us a bit of what you do, and most important, could you tell us a bit of how the others can help you to it even greater?
I mean, just we are interested in partnership with a producer of, let's say, micro mini LEDs that are, of course, suitable for the lighting application. So we are talking to white light with good spectrum and sufficient lumen watt and Eurolumen figures that are okay for the lighting. Of course, miniaturizing the sources in the first approximation allows to miniaturizing the entire device. So being aware that finally with the decreasing the source size, the thickness, and therefore the volume of the device will be less, and ultimately the prices of the raw material will scale with the volume. Obviously, considering the scale up of the production, one can foresee a significant reduction in cost for mass production. So definitely the miniaturization of the source is the way to work at in order to create artificial skylight that are sufficiently say small to fit all the spaces, ranging from residential to automotive, and also to on mass production, let's say, million units volume, end up with cost that are really fit in the market. So definitely is the way. No, there's no another way. And we are interested to cooperate with any company who would like to take the challenge of producing, let's say, micro mini LEDs that are for application in light, ranging initially even with say mid power, not necessarily to go to very high brightness, but of course go in that direction finally.
Let's go to the market leader, Paolo, because then we go there and then we can, of course, go to the more niche companies. But the market leader, AMS, Osram, Wim Hertog, you saw the challenge of Paolo when it comes to the mini LEDs. He needs a reduction of the size. And of course, remember that this application also requires certain amount of power. What is the first thing that comes to your mind when you get this potential customer to your place? What is the first thing that you would like to ask back to Paolo?
So I know Paolo's work from previous meeting we had here at EPIC, and so my question would be, Paolo, it seems that you need a lot of light for this application, right? A lot of flux. And this will be a big challenge with micro and mini LEDs. Is your system limited by, so the miniaturization of your system, is it limited by the optics size, or is it more of a source issue, or is it a combination of source and optics at the end? How do you want to miniaturize your final product if you have a smaller source? That would basically be my question.
Yeah, actually, the first question you ask concerns the amount of lux, so that, let's say, the lux that finally you need to get it out. Of course, if you consider lighting application, you might see that the number could be pretty high. But is it clear that technology will evolve in that direction, and therefore starting from some applications that are not necessarily related to the let's say the residential or the building industry, for example, in the transport area, where the amount of light is not necessarily always very high, it's possible to bridge this gap slowly. Even mid-power level could be suitable for application that will be able to run over, let's say, 100,000 units per year or even more, which are already big numbers. The optical layout that is suitable for reaching the infinite effect, infinite depth of view effect that we managed to create with larger devices in a small scale on the display level. It's quite sophisticated. There are many solutions, and I think we can talk now about a few options that are under development, and we already have some preliminary prototyping and devices. So there is possibility to work on that. But of course, the driver is the size of the emitter.
We have a comment on that from Cliff Jolai from PI, Physics Instrumental. Cliff, what's on your mind?
Yeah, it was just a comment about some of the pitch, and I think one of the questions or comments is the pitch of the micro LEDs is not to be confused with the accuracy of the placement. But I believe that Alexander from ALOS has also mentioned that he's seeing applications where the pitch is down at 1 micron as well. So it really depends on the application. So that's just a comment.
Alexander, tell us.
Yes, we do see. I mean, there's of course many different applications, and the need for the in a way pixel density. I think that is the determining factor is driving this. But we see on our customers, we see people building pixels which are significantly smaller than 1 micrometer square. I mean, really significantly smaller, and the pitch is less than 1 micrometer.
At the end of the day, this will have to be standardized somehow, right? At the end, you cannot really develop a process for each one of your customers. Do you see a transition to standardization of the pixel size?
No, I think this is really very much application and solution driven. We heard comments earlier on how you do the light out coupling from the chips. I think that is also then really dependent on what people do. I mean, and with these small pixels, we're obviously talking about extremely high pixel densities for typically augmented reality displays. But even for chips which are 5 by 5 micrometer, we see that the pitch, or rather the gap between the pixels, is shrinking very dramatically, and that is of course then something which can be done with CMOS processing lines. And that I mean, people who work on these kind of small chips use CMOS lines for the processing.
I do believe that at the end there will have to be a little bit of a standardization. One, because we are talking about the testing, and without standardization, testing is very hard. Gerlob, we talked in the beginning that they are working with many suppliers. They really have to have a certain idea about this. But most important, from presentation in the beginning by Soeren, what we have seen at the end is that they want to scale up a product that can actually manufacture 300 millimeter anywhere in any production line. Soeren, when it comes to the pixel size, Soeren from MICLEDI, when it comes to the pixel size, and do you see that eventually there will be some kind of standardization for the pixel size in the AR market?
No. I don't see that there's a need for standardization. It will be in the end like a design kit for, let's say, a PDK specific for a foundry, and that will be allowing then between, let's say, 1 to 3, 4, 5 micrometer, depending on the application, to integrate. And of course, as smaller you make the pixel, as more your losses will be. There's no doubt about it, and as more difficult it will get to integrate efficient optics. So for every application, maybe now viewfinder or AR or VR, you will probably have let's say, own the set of design rules, as well as the way how to integrate it with the CMOS and the way how you make a wafer level optics.
We have a person here with a nice comment. The company is called Photonics, all the way from Eindhoven. They make roll-to-plate nano imprint machines. And Erhan has something to comment. Erhan, what's in your mind?
Hey, Jose.
Hi, Erhan.
Hey, no, I mean, I was just making the comment that basically if you want to go, I'll start my video, sure. My laptop was turned off, but okay. You can hear me, you can see me. Yeah, what I was saying is that if you are trying to go with a pixel pitch that is going to range between, up to 100 microns, yeah, that would be considered a micro-LED. Anything beyond that would be a mini-LED. That seems to be the threshold, but yeah, I mean, it's just going to depend on whether this is a direct view display or a display like a micro display that needs to be used and projected through some optics.
Erhan, could you tell us in one sentence or two what you do? Because I really want everyone to be part of the MicroOptics European revolution, and you are one of the examples of success.
Yeah, so what we do at Photonics, as you're putting out on the screen right now, is very large area nano imprinting. What we do is structures that range from 500 micron down to 15 nanometers, and we can replicate these structures very reliably in these large areas of greater than 1 meter square. And we can do all kinds of different structures. If you have thought of it, we probably have replicated it. So that's essentially, what we do at Photonics.
Roll-to-plate manufacturing of almost any structures. You're doing a fantastic job. You are one of the companies that make us proud of this MicroOptics revolution. We have two people who want to interact. First, we have a comment from Osran about the pixel size. Wing?
Right, yeah, I was just thinking that pixel size does not necessarily has to be connected to the size of the light emitting part, so the emitter size, for example. I can imagine that you have a relatively large pixel size, for example, for a TV, but within that pixel you can have a very small RGB based emitter that's emitting the light, and then the rest is just black space, basically. And that should work as well. And in that way, you can have a standardized process that fabricates really small emitters for all applications. And then depending on the application, you have a larger pixel pitch or not.
And the last comment of this great meeting, by the way, great meeting. Thank you so much for your interactions today. You were all fantastic. The last comment comes from a friend of EPIC, Chenglin Xu. Chenglin from Synopsys. Tell us what's on your mind.
I think I heard quite a few times about the PDKs. I think my view is to design any photonic device, including, of course, a micro LED, and the design tool which built-in PDK from foundry is essential, and for the designer, and I think that is very, very critical. So, and we need. For Synopsys, maybe can share a screen? And
yes, always.
Yeah. And just to give you a little bit of introduction, and Synopsys, and just in case, wait a minute, I didn't click, double share, let's try. And for those you don't know Synopsys well, and Synopsys is number one, the biggest EDA company, electronic design automation company in the world, and which about I think it's $4.2 billion revenue in the past year, and over 16,000 employees all over the world in 125 locations. And of course, mainly the focus is for Synopsys is the electronics EDA, right? And also starting in 2010, that's 11 years ago, and Synopsys is moving into MicroOptics, Photonics. And down the road, in the past 11 years, and Synopsys acquired 5 different companies, or in different aspects, and the best in this field. And for me, and I working originally at Arsoft. It is founded in 1990. It's more than 30 years ago. That is the first photonics design tool company. And in the past, of course, we develop all different design tools for photonic device. And one of them is related to this topic is I call LED for LED utilities. It is designated tools design and simulate LED device, of course, including micro LEDs. There are 2 types, and generally speaking, one is a 2D thin film type, and like this Facebook proposed, and this is the pattern, and also like a 3D nanowire type. And this is the LD, I hope I pronounced correctly. And this is a 3D nanowire type. And the basic algorithm is use a full wave FDG to the simulation and do the pre-processing input data and also post-processing simulation data to get what you need. We are able to calculate this extraction efficiency because I hear quite a few times the efficiency is very important for this micro LED, and we are able to calculate the extraction efficiency both going upward and downward. And we are able to calculate the far field pattern in homogeneous media. And this is, to my best knowledge, this is the first ever in commercial software. And we just implemented this feature in the last release, actually. This way, we can get this far field pattern both in the upper in the air and also in the downward in the substrate. And you can see clearly and how the radiation pattern looks like. And so I think the common question and so what we can do for you guys, and of course as a design tool company, and we can help you your design to shorten the developing cycle and reduce the cost and validate your design. We are not doing design, but we are helping you validate your design. And what you can do for us, and of course, we need to know what kind of problem you are working on, and share with us what kind of problem you have, and we may be able to find a solution for you already on the shelf. If not, and we will do our best to develop one for you. Thank you very much.
Thank you very much, Henry. And I have to say that from the beginning, when Synopsys joined EPIC, you have been connecting lots of companies on the design side, and you're doing a fantastic job for us. Thank you so much, Synopsys, for being a member of EPIC. I want to close the meeting the same way it started. I want to go to one of our success stories in micro displays in EPIC, which is 4-dimensional display copying. And Greg Truman, tell us what's on your mind, what has been maybe your takeaway from this discussion, and send us off the way that we deserve.
I'm just going to really comment on the pixel pitch for micro displays. Micro displays are funny things. They're basically a whole series of compromises. There is no perfect micro display of any technology. You're compromising size, the materials you use, bandwidth, all those types of things, light distribution. But when it comes to pixel pitch, if you do the maths, you will quickly come to the conclusion that somewhere around 9 to 10 microns is about the maximum pixel pitch you can get away with. There are people doing a lot less in some technologies, but 9 to 10 microns is about the maximum. If you then look at a spatially separated RGB technology, doesn't matter what technology it is, any spatially separated RGB technology, you're either going to have to do 3 strips RGB, or you're going to do some sort of RGBG type arrangement or something like that. And that will then drive your pixel pitch for each subpixel down to 4 to 5 microns pixel pitch. You then need various areas around it. So if you want to do a standard, I would suggest if someone wanted to do a standard LED for micro displays, they should be looking at something in the order of 1.5–2 microns, something like that. And then obviously that can be spaced out, or the gaps increased or reduced depending on exactly what you're trying to do. But that's probably the direction to go if you want to do it, if you want to standardize at least part of the structure for micro displays.
Greg and everyone, thank you for one of the best discussions since we started with the online meetings 120 meetings ago. This was one of the best. Thank you. Thank you so much. And that concludes the public part of today's meeting. If you are in our Zoom room, our informal private discussion is about to start. I call it virtual drinks with friends. And we all know follow-up is important. But for now, if you are watching on YouTube, that's where we leave you for today. Thanks to the epic production crew and our sponsors for making today's event possible. More details about upcoming meetings are on our website. And if you want to get in touch with any of the participants, all you have to do is contact me directly and I will make sure you get introduced. It is all about connections. Thanks for being epic.